Very good day, friends. It gives me a great pleasure to record this presentation, particularly at a time when we are all passing through incredibly difficult period of our life. All of us are in a lockdown mode, house arrested almost. I wish you and your families well and advise you all to please stay safe and stay at home. This is a presentation which I had, in the form of a webinar. It was given a couple of days back to the platform of IAStructE. Unfortunately, at that point in time, this presentation was not recorded, and I was requested by many to record the presentation and circulate it through YouTube, and that is the reason why I am recording this presentation now. This presentation, let me tell you, is a sequel to an earlier presentation made by me way back in December 2016. And that was on the topic of bridge bearings, state of the art, wherein I explained in detail about the bridge bearings, various types, its function, properties, possible arrangement, what should be done under what circumstances, how the new limit state code for bearings have to be applied. And it was a pretty detailed presentation. Anyone who is interested to go through that presentation, I can send the link, and if you just Google bridge bearing state of the art, probably you'll be able to locate that in the internet. With this, let me start on my presentation. Which is on the topic of lessons learned from bridge bearing failures. We have seen number of existing bridge failures in the recent past, and in recent past means over last about decade or so. And many of these bridge failures are attributable to the failure of the bearing. What you see in this slide is some examples of bridge failures caused by bearing. The the figures, these three bridges which is shown here in this slide is not the true reflection of the number of bridges which fail due to bearings. Let me mention that there are number of bridges where during the installation of the bearing or during couple of months after installation, the problems have arisen and the bridge bearings have been replaced, but those do not come to limelight because that is the period of defect liability or during construction where the contractor, the client, and the consultant, all of them, do not try to highlight the failures, and therefore they are simply replaced. The bearings are replaced without really informing the public at large. What you see here in this slide on the top left is a famous failure of Ultadanga flyover in Kolkata, which happened in 2013, just about 2 years after the bridge was open to traffic. One of the span, which is a curved span, which is sharp radius, it toppled in the middle of night when simply a truck was passing over this bridge. And then after detailed investigation, what was found is that the bearings were not installed properly. And this is a very interesting case where, because of the curvature, the one of the bearing on the inner side was a tension bearing, which is called knuckle bearing. But during installation, by mistake, the contractor installed it the other way around, which means the knuckle bearing was installed on the outer side rather than on the inner side of the curve, and the result of which was the toppling of that particular span with hardly any load on top of it. What you see on the top right is the famous airport express line in Delhi, where some 688 number of bearings had to be replaced, which is for 86 spans, all elastomeric bearing, and they all had to be replaced because they were originally installed uh, very poorly, which resulted in vibrations and problems with the performance of the bridge. The airport link had to be, you know, the operations on the airport link had to be stopped for nearly a year for this repair, and a huge cost of the bridge bearing replacement had to be incurred by DMRC. What you see on the bottom left is a collapse which happened quite recently. It is in 2019 December, where it is not exactly the failure of the bearing, but the failure of the bearing support. That means the cantilever brackets were not adequately designed for the bearing loads, and it collapsed after 7 years of operation. Uh, we, I mean, this is not the presentation where we go into the details of why it occurred, but suffice it to say that it was inadequate design. The reinforcements were grossly inadequate in the bracket, and which caused the collapse of the whole bridge. Uh, Before again I get into uh, the bearing failures, let me just make a little just gloss over the certain basics about bridge bearings. The main function of the bridge bearing is to accommodate translation and rotation caused by the in-plane and out-of-plane movement and rotation of the superstructure due to various loads. Bearings transfer vertical and lateral loads from the superstructure to substructure and foundation, while it releases the translation and the rotations. That is the main function of the bearing. Uh, uh, Vertical load will get transferred whether you have bearings or not, whether you do not have bearings. As an example, in buildings, we do not provide bearings in majority of the cases because the spans are of the order where the rotations and the lateral loads caused by the deformation are not so significant. But in bridges, where the spans are long, the rotations and the translations are going to have significant effect on the substructure and foundation in case you do not release those deformations. And that is why the need for bearings. The type of bridge bearings are many. I mean, since middle of the last century, many modern bearings have come in. Uh, Prior to that, most of the bridges we used to provide, metallic rocker and roller bearings, but today rocker and roller bearings are becoming out of date, and the other modern bearings, which are called HLMR, that is high load multi rotational bearings like pod bearings, disc bearings, spherical bearings have come into existence, and they are performing. We also have the elastomeric bearings, which are very popular for short and medium span bridges. And then we have special bearings, which are, uplift bearings or restraint bearings, which helps in, better seismic resistance. And you also have isolation bearings, which are quite popularly used. Uh, One thing I wish to tell you now is that the modern bridge bearings are far more complicated structures as compared to the historical ones. They are, because of the progress, technological and scientific progress, these bearings can take much higher loads for a much smaller size, and therefore the stresses are quite high. Now, these would mean that the modern bearings are much more sensitive to accuracy in design, in installation, in manufacture, as compared to the bearings of the past. And this aspect needs to be taken into account while designing, while manufacturing, and while installing the bearings. Unfortunately, the bridge bearings are still treated in the industry as a construction product, as a civil engineering product, but in reality, the bridge bearings are actually mechanical devices where the tolerance requirements are far, far too rigid as compared to the tolerance requirements of civil engineering structures like your, structural elements like foundation, substructure, superstructure, etc. This differentiation needs to be respected by all, and that would only be the solution to get a quality bearing. The primary function and the operating principle of bridge bearings are shown in this slide. As I mentioned earlier, the bearings are devices which allows displacement and allows rotation and only transfers the vertical load to the substructure and lateral loads also as per the designer's choice. Now these displacements can be achieved uh, at the bearing locations by three mechanisms. One is the sliding, one is rolling or rocking, and the third is deformation. Now, a sliding mechanism would mean that the provision of a sliding element like PTFE or UHMWPE, any sliding material uh, by which the top part of the bearing, which is connected to the superstructure, will move without uh, offering any resistance as compared to the bottom plate. The second mechanism for displacement is a rolling mechanism, which concept is being used for rocker and roller, where the top plate rolls over, and in the process, the movement is allowed, and the roller also will move half the distance as compared to the movement of the superstructure and the substructure being rigid. The third the third method is by deformation, which is a concept which is used in case of elastomeric bearing, where the elastomeric bearing, the top moves with respect to the bottom, and thereby there is a shear deformation. And this kind of deformation will attract some force to the substructure and foundation, but bearing being quite flexible, the elastomeric bearings, these forces are catered for in the design, but they are not significant. Similar to displacement, the rotations also can be taken by three distinct mechanisms. One is the sliding mechanism, which we see in case of spherical bearings, where the top plate has got a curvature and it slides with respect to the bottom surface, which is also curved. Second is the rolling mechanism, where there is a rocking arrangement and the top plate simply rotates with respect to the bottom plate. And the third is the deformation, where a pot bearing is based on this concept, where the confined elastomer is allowed to rotate. Of course, this rotation in this case is little restricted as compared to the rolling mechanism or the sliding mechanism. Uh, this slide shows the example of the world's longest, largest sized bearing, which happens to be in India, in Delhi. This is the signature bridge, where world's largest bearing has been installed. The spherical bearings, as you see on the right hand side, is of diameter about 2.8 meters, 3 meters, and it can take a load of 23,000 metric tons. This is by far the world's largest bearings. These bearings were manufactured, fabricated in Germany under strict quality control. The one of the problem of this size bearing is that these such bearings can never be replaced, unlike the conventional bearings which are designed for replacement. So these bearings have to have the same design life as that of the existing bridge, and maybe a little more. So therefore, a very high level of quality control, precision is required in manufacture, in installation of these bearing and also in maintenance of these bearings. Uh, why bearings should have a higher margin of safety? I think this is an important point, and bearings are, as we all know, are vital elements, and uh, cost of bearings are actually minuscule of the total cost of bridge, and therefore, then it is always important and prudent to be little liberal in designing the bearings. It should be robust, and many a times, replacing a failed bearing costs much more than the original cost of bearings, and therefore the bearings should be designed, manufactured, and installed with a lot of margin, so that there is no scope for any error. The need for quality installation and inspection practices are often overlooked, and this is the main problem because of which the bearings becomes the reason for failure of bridge many a times. Now, let us come to the details of my presentation. The principal causes of bridge bearing failures can be really divided into three groups. One is the design fault, second could be the manufacturing fault, and third is the fault due to faulty installation. Now let us come to the design fault. There could be uh, primarily due to three reasons. One is due to lack of experience on the part of designer and reviewer. Unfortunately, not many literatures and books are available in the market which explains in detail what are the do's and don'ts in case of bearing design. So there is a fair chance that the design forces, movements, and rotations are underestimated by the designer, and which results in faulty design of bearings. Incidentally, the design of bearing is done by two independent, uh, organizations. One is the design done by the bridge designer who is involved in the bridge project. He or she estimates the design forces, movements, and rotations, and prepares the bearing layout. And this drawing is passed on to the bearing manufacturer or vendor, who does the detailed design of the bearing, and then this is based on this detailed design, the bearings are manufactured and installed. Uh, the second possibility could be improper choice of the bearing type itself. That means the layout of the bearing is faulty. Uh, and also the faulty bearing layout in plan of the bridge structure can, cause serious issues. Let me tell you that many a times these underestimation of design forces or faulty design is by error of intent, done by some vendors in order to save initial cost. And particularly in an EPC mode of contract where each and every penny counts for the contractor, uh, this is a very dangerous practice which we have seen, and therefore the people who are doing the proof checking or the independent review, they have to be really very careful, and checking of designs is extremely important. These are some of the references I would like to advise all listeners of this presentation to closely follow. Try to get these literatures, and this gives you a lot of idea about how the bearings are to be designed, how the bearing layouts are to be done in a structure, and what are the important parameters which needs to be taken into account by designing the bearings. I would recommend all the bridge designers to have access to any of these or maybe all of these for their reference. Uh, so, if underestimation of design forces and dimensions, there are many good examples which I can quote. One good example is the collapse of Surat flyover. It's a classic example of wrong design, which led to failure of this flyover during construction itself. This Surat flyover uh, collapsed in June 2014, killing about 10 people. It was a simply supported curved bridge of very sharp radius. First mistake was to have a simply supported span for such a sharp curvature. That is not recommended at all. When you have a curved span, normally the uh, the the good practice is to have a continuous structure rather than a simply supported structure. But having conceived it to be a simply supported structure, the design should have been done properly, ensuring equilibrium as well as the correct uh, estimation of forces. In this case, after the collapse, detailed investigation revealed that the designer simply designed this curved bridge as a straight bridge, calculated the forces, and at the end of all the calculations, he simply added 25% to account for curvature. Now, this is a gross error because the behavior of a curved structure is entirely different from that of a straight bridge. In case of the curved superstructure, the forces in the bearings were coming in the to be negative, which means you had to anchor the bearing. You had to provide a tensile bearing, which will hold it against toppling. But instead of that, if you design it as a straight bridge, you will get compressive force and you add 25%. That means you have provided a completely different type of bearing than what is required. And this is precisely the reason why this particular span collapsed. So it is a good example of how uh, the ignorance of the designer can lead to this kind of mishaps. Another example I would tell you about, you know, uh, is the long span bridges, particularly in long span bridges where you have the central hinge. Oftentimes, I found that the estimation of rotation for the design of bearing is underestimated. When you have a central hinge for a long span bridge, the central hinge has to cater for the double rotation, that means rotation from the two ends. And these rotations have to take into account not only the rotations caused by the live loads, but also the creep effect of the dead load, pre-stress, etc. And this calculation is quite complex. In many occasions, I found these calculations to be grossly in error, and the proper estimation increases the rotation by many fold. So I think it's very important that these are assessed properly. Uh, when it comes to long span, I am again showing you some of the slides of Signature Bridge Delhi, and the reason why I am showing Signature Bridge is this is any bridge of long spans where the forces and the rotations are of very high magnitude. The chances of error are also very high, and considering the sensitivity of this element, I think as the span increases or as the load on the bearing increases, the degree of checking review is required is much more. It increases in the same proportion. This is an example of what happens to the PTFE in a pod bearing when the edge pressure is too high, when the pressures on the bearing is underestimated. You can see this failure where the PTFE simply flew away, leading to contact between steel and steel and increased friction. Uh, the Just for information of those who are not familiar with pod bearing, pod bearings was first used in Germany way back in 1958, and it became very popular. Uh, in case of a pod bearing, an elastomer is placed inside the steel pod, which is a confined elastomer, and the it presses the top of the elastomer when the vertical load is applied, and on the top plate you have the PTFE sheet. On top of PTFE sheet, you have the stainless steel plate, and the friction is reduced by the the contact surface between stainless steel plate and PTFE plate. And what we are discussing here is the increase of stress in the PTFE, which resulted in crushing of the PTFE itself. This is another example of underestimation of the design force leading to failure. In this case, you can see the elastomeric pad, which is simply walking away, and this walking of elastomeric bearing happens when the minimum load is very low, and the friction between the elastomer and the concrete, it depends on the vertical load, and the lower the load, the less is the friction. So this is a scenario where if you overestimate the minimum load, then there is a problem of walking away of the elastomeric bearing, and this is one such example. Third example is again I put back again this Karamnasha bridge, where I mentioned this failed in December 2019, and it is not the failure of bearing actually, but it is the failure of the support to bearing. And you can see here that there is hardly any reinforcement in the bracket, which has caused failure. In fact, what is surprising to many people like us is how this bridge could survive for 10 years without any reinforcement. And I think the credit must go to the contractor, who must have given a very good quality concrete. And so far, for 10 years, this bridge could survive because of the tensile strength of concrete. Uh, uh, there are the types of modern bearing, can be broken up into three parts. One is the elastomeric bearing. Every kind of bearing has its own range of application. For example, the elastomeric bearings are meant for short and medium span bridges. Second category is the uh, high load multi-roller bearings, which comprises of pot bearings or disc bearings or spherical bearings. They are used for medium and large spans in a wide range of load bracket. And the third one is the metallic roller and rocker bearings, which have limited application in today's scenario. The choice of bearing depends on many factors, uh, like the types of structure, whether it is a highway or the railway, what is the total magnitude of vertical load, maximum and minimum, what is the maximum rotation, what is the horizontal displacement, environment, economics, and structural arrangement. So there are many examples of bridges where the wrong choice of bearing has been adopted, and subsequently it led to problems. As an example, I can quote that in all the recent expressway projects in India, spherical bearings are abundantly used even for short spans of 15 meter, 12 meter or so. And this is being done since one of the IRC manual for 6 laning for expressway mentions about a design service life of 50 years for bearings. I think this is not the correct application, and the bearing should, depending upon the span and the load, appropriate bearing should be actually chosen. This is one guideline which tells you what kind of bearings to be selected in under what circumstances for what vertical load range and what capacity. It's a fairly good table which helps the beginners to decide on the type of bearings to be proposed, depending upon the vertical load range, depending upon the rotation, depending upon the translations and the geometry. Uh, the Now let me come to the faulty layout plan of bearings, which could be one of the reasons for failure. There are several bearing layouts. Let me first start with the simply supported spans. There are several bearing layouts for simply supported spans which are in practice. Not all of them are, however, desirable ones, and some of them suffer from serious drawbacks. Unfortunately, we do not have any guidelines so far in IRC which guides the designer as to choose a particular type of bearing layout, and it is all left to the ingenuity and the experience of the designer who is performing the design. Uh, Fundamental principle in fixing the bearing layout is essentially to ensure that the load transfer from superstructure to substructure is symmetric and the locked-in stresses are reduced to minimum. And you can see here there are so many possibilities that exist. For example, if you have a narrow deck, normally you will have narrow deck means about 2-lane or 3-lane bridges. You will normally have two bearings on each line, and one will be in the fixed end. You will have a fixed bearing and a metallic guided bearing. On the other end, free end, you will have a metallic guided bearing and a free bearing. This is one possibility. The other possibility could be to have the vertical loads taken by 4 set of bearings, and the lateral load is segregated by using pin bearing and metallic guided bearing. And the third option could be to have a free bearing instead of a guided bearing here on one side. Now let us go into the details as to which one should be done. Uh, the Let's take the case which is very often used by many designers all over without questioning. That is a layout where a fixed bearing is used at one end, and a metallic guided which you know allows translation in the transverse direction is being used here. And on the free end, you have a guided bearing which allows longitudinal translation and a free bearing. Now, this is a very classical approach, but it suffers from some drawbacks. Number one, the sharing of lateral load between the two bearings are never uniform. As I mentioned earlier, that the fixed bearing and the guided bearings, they have different tolerances, and therefore when the lateral load comes, the share is never equal. All the loads will be taken by the fixed bearing, and only when there is a deformation of the fixed bearing, the other bearing will start effectively sharing the load. So this is one drawback. And the second drawback is the horizontal forces in the cross direction due to wind or temperature difference can cause horizontal restraint forces where the deflected pattern you can see is not symmetric, and this is also a disadvantage. The better option or the new approach is to have a free bearing here instead of a guided bearing. And you can see that if you do that, then there is no doubt that the entire horizontal load has to be taken by the fixed bearing, and but there is symmetricity in the lateral deflections, and there is no ambiguity as far as the load share is concerned. So this is better, but this is not the best. In fact, the best solution would be to have free bearings at the ends and the central pin bearing and a metallic guided bearing. Because in the previous option, if you have the entire lateral load taken by the fixed bearing, this will lead to some torsional forces in the substructure and foundation, which is not desirable. But in this case, you can probably avoid the torsion in the substructure and foundation. So this is a better option. Now, let us come to another case of skewed bridges. If you see layout in case of a simply supported skewed bridge, you can have a similar arrangement where you have a fixed bearing and a free bearing in the fixed end, and a free bearing and a guided bearing in the free end, at the free end. But where should we have the fixed bearing in this case? Should it be at the acute corner or at the obtuse corner? Well, the correct solution is to have this fixed bearing at the obtuse corner, and the reason being that the reaction on the obtuse corner is much more than the reaction at the acute corner, and a higher vertical load is always better for the bearing which is carrying lateral load, because the uh, horizontal load, the inclination of the resultant load will be close to vertical in case the fixed bearing is at the obtuse corner. So layout option 2 is a preferred option. Let us take examples of few continuous spans with high load multi-rotational bearings, and you can see that fixed line of bearing can be placed either at one end or else at one of the middle piers. I mean, the choice is that of the designer. Arrangement of all other bearings depends upon the location of the fixed pier. And high load multi-rotational means, high load multi-rotational bearings. And you can see there are so many options possible. Uh, this is the preferred bearing layout for straight continuous bridges. You can see fixed bearing can be here, and at all other free piers you can have guided bearings, which is aligned with the fixed bearing, as you can see here. For curved spans, continuous curved bridges, there can be many options for choosing the bearing layout as shown in this slide. Location of the fixed point, that is zero movement point, is important, and that decides the orientation of the guided bearings. Those who are not familiar, let me just quickly explain that in any curved continuous deck, once you choose the location of the fixed bearing, then the location or the direction or orientation of the guided bearing in all other spans will depend upon the location of the fixed bearing. And as you can see, if you draw a line connecting the fixed bearing the with the bearing at another pier, along the same line you should have the guided bearing orientation in order to avoid any uh, stresses caused by the deformation of the structure due to thermal induced or shrinkage or pre-stress induced forces. Now, therefore, considering this fact, there can be two or three options as explained here. Option one is where, which is quite commonly used in the industry, but it suffers from one drawback. And the drawback is the expansion joint at the other end where the fixed bearing is not there. The expansion joint here moves both in the longitudinal and in the across direction. And as you may be aware, that expansion joints function much better only when they are allowed to move in the longitudinal direction. Their cross direction movement capability is far too less, and therefore for longevity of the expansion joints, it is always better to avoid any cross movement in the expansion joint. From that consideration, option one is not a good option. The other option, second option number two, if you see, it solves the problem which we discussed in option one, but it increases the undesirable temperature forces in bearings and substructure. In this case, what is done is the principle followed here of aligning all the guided bearing with the fixed bearing was not done, and then that would obviously result in induced forces due to thermal and shrinkage forces, which will be quite high, and therefore it comes at an expenditure. The third option is the best option in this case, where you align the uh, bearings uh, at the other end. First, you decide about the alignment of the guided bearing at the expansion joint end by aligning it longitudinally or tangentially, the guide tangentially. And once you determine this alpha, then you orient all the other guided bearings by an angle alpha. And if you do that, then also the thermal induced forces are reduced to zero, and it serves the purpose of aligning the expansion joint in the longitudinal direction, but at the same time avoiding thermal induced or shrinkage induced forces. So option three is the best option in this case. Uh, Another problem that we face for in the bearing design is the faulty fixing detail of the bearing. We have seen in at many occasions that the designer simply designs the bearing, and when it comes to the detailing of the superstructure at the junction of bearing and superstructure, or detailing of the pedestal, uh, simply the interface is forgotten about, and this is a very serious issue. On many occasions, I have found at site that the pin bearings, while installing, the contractor finds it very difficult because the pedestal reinforcement fixed do not allow for the provisions of studs to get into it. You can just see an example of a typical bearing where you can see so many studs are coming out, and these are to be embedded in pedestal. Unless the reinforcement detailing in the pedestal takes into account the location and the direction of these pedestals, unless that thought process has gone into the bearing designer uh, mind, you will never get a good solution. So the lessons learned from here is that the designer of the bearing must also ensure that the connection of the bearing to the superstructure and the pedestal duly takes into account the fixing arrangement of the bearing with the superstructure and the pedestal. In many occasions, I found that, for example, if you have a steel structure, steel superstructure, then the connection detail of the top plate will be entirely different from the connection detail of the bottom plate, because the bottom plate will be fixed into concrete pedestal and the top plate is supposed to be fixed to the steel superstructure. In many occasions, I found that the bearing vendor has simply given the same detail as that of a concrete, irrespective of whether the structure on top is steel or concrete, and we had to refer back to the manufacturer vendors to also tell them, apprise them that look, you have to change the detail. So I think this is an important parameter which should be kept in mind. Now let us come to the second part, which is the manufacturing fault, which causes the bearing failure. Manufacturing fault can be because of poor quality of material, because of non-respecting dimensional tolerance, or because of the improper corrosion protection. Poor quality of material refers mostly to elastomeric bearing, which are made of compounds containing a great variety of components. Uh, as far as the metallic bearings are concerned, the quality issues of the material per se do not really come into the picture. Raw elastomeric material in the bearing can be, as you know, chloroquine rubber or natural rubber of different grades, as mentioned in the code. The effective use of rubber as an engineering material actually depends on the understanding of its behavior and its chemical composition. Unfortunately, we as structural engineers or bridge engineers, we have very little idea about the rubber technology, whereas the elastomeric bearing manufacturing involves a lot of rubber technology, where the elastomeric bearing properties that we achieve depends on a complex composition of the materials that is combined here with, but that is an area which is Greek to the civil and structural engineers. What we need to understand regarding elastomeric bearing is that it's a viscoelastic material. It is neither elastic nor plastic. And we need to know a little bit about what is viscoelastic material. You see, normally the steel and concrete that we deal with in the normal force stress range, they are elastic. That means within the elastic range, the stress is proportional to strain, and when you release the force, it comes back with no plastic deformation. If it is a plastic material, then when you release the force, then there is no regain of the strain, and the strain is permanent. When you talk of elastic plastic material like metals, then at the when once the yield line is crossed, then if you release, then there will be some permanent strain, inelastic strain. Now, elastomer is such a material which is viscoelastic, where the stress strain diagram is not linear, unlike your elastic plastic material like metals. It is viscoelastic, it is a non-linear characteristic, but the beauty is when you release the forces, then it comes back to its original position and there is no permanent strain. And this is one characteristic which helps us to use elastomer as a bridge bearing material. Uh, Elastomers are, as I mentioned, a complex polymer compounds which have mechanical properties that are sensitive to changes in compounding and vulcanization process. They are flexible in shear and in uniaxial tension or compression, but very stiff in its volumetric deformation. The material properties are non-linear and time temperature dependent. Thus, factors such as creep and low temperature stiffening are important to the designer. Uh, the problem with bearing manufacture of elastomer bearing manufacture is that they have large mass of rubber, and it is difficult to get a uniform cure throughout the cross section of the elastomer. Uh, Vulcanization process has to be very, very controlled. If it is too long, the outer edges of the pad becomes brittle due to overcuring. Conversely, if the curing process is cut short, the center of the pad remains uncured, resulting in excessive deflection under sustained load. Now, you see, the elastomeric bearing is one such material which, if done properly, it is in fact one of the best bearing type, which has got very good resistance against the earthquake, and therefore I would strongly recommend use of elastomeric bearing to the maximum extent possible. Uh, as long as you are able to satisfy all the requirements of elastomeric bearing. The problem in India is that most of the people they give a feedback that the manufacturing of elastomer, there is a lot of problems with the workmanship and the performance of the elastomers that we get in India. And I think this is one area where uh, the manufacturers have to really uh, make sure, if they want to survive, if the elastomeric bearing has to survive in India, then the manufacturers have to come out and solve this problem of quality. Uh, Bottom line, as far as the structural engineers are concerned, because as I mentioned, we are not rubber technologists, so we structural engineers only understands the few properties, the physical properties which influences the behavior of elastomeric bearing. So we only see the end product and compare its hardness, its tensile strength, its elongation at break and compression set, and decide whether the elastomer is performing or non-performing. So these are the end requirements of structural engineer from the elastomeric bearing. But I would wish that a bit of rubber technology structural engineers involved in the bearing design should know, because that helps them to inspect and accept or reject a material. Uh, you know, when the manufacturing process, when you are selecting a raw material for the last one, when you are inspecting the quality assurance or factory production control, or you are accepting the bearing, a little bit knowledge about its technology of rubber and composition helps a great deal. Uh, we have seen number of failures of bridge bearings, elastomeric bearings, due to poor manufacture or poor installation. I mean, these are few examples. Cracks observed on surface of elastomeric bearing, uh, and many of these occurred just after the installation and immediately got replaced in matter of 2-3 months after correction. Uh, Coming to the failure or non-respecting dimensions and tolerance for metallic bearings, we can see that non-respecting dimensional tolerance is a common fault in case of metallic bearings. Some tolerances are very important for reliable bearing behavior. They concern mostly the mechanical bearings. The gap in the PTFE sheet recess should not exceed 0.6 millimeter in common situations. Otherwise, the PTFE sheet can be easily extruded from its recess during the bridge span movement, as you can see in this particular sketch. Uh, Very important in bearing sliding element is proper choice of PTFE sheet, lubricating agent, and respecting roughness limits for sliding surface and mating element. All that is not covered in great detail in the codes, but I think the experienced vendors and the experienced inspectors of the bridge bearings would know. Many a times, due to lack of dimples in the PTFE sheet, and additionally the use of silicone oil in place of silicone grease, the frictional resistance can be as high as 10 times more than the case of properly chosen material, which can lead to failure. Uh, Sometimes it happens that the vertical clearance in the guide channel between the central shear key and the upper sliding plate is insufficient, and the shear key is immobilized, and its linking bolts are cut. As PTFE sheet is subject to wear during the bearing movement, its depth becomes lower and lower, and there is a reason why the clearance between these two elements should be designed with sufficient gap. Uh, Otherwise, the elastomer pad can be extruded through the gap between these two elements, as can be seen in these two sketches. There is also, a possibility of the elastomeric pad extrusion when there is an excessive deformation which is caused by high horizontal lateral forces during construction. As I explained earlier, that if during construction stage proper care is not taken, the bearing forces, lateral loads can increase to a very large extent, and that can cause failure of the bearing during construction stage itself, as you can see in this particular slide. Uh, Sliding element and sealing ring in pot bearings as well as in shear keys in all guide bearings are the most vulnerable parts of pot bearing. Many a times uh, this there can be locking because of the lack of adequate clearances, which can cause uh, blocking of the shear key. And what you see here is, you can see that there is no gap. There should be a gap here to allow free sliding of the top plate as compared with respect to the bottom plate. This is not happening here because the adequate clearances are not given. Uh, Now, coming to corrosion protection, uh, this slide shows that the painting in the superstructure and the pedestal has covered the elastomeric bearing also, which is totally unacceptable. Uh, for elastomer, every paint cover may be very dangerous for material behavior, especially when it contains aggressive agents for the rubber. Sometimes it happens that painting cover is used as a mask hiding cracks on elastomer surface, and that should be prohibited. So one must be aware that when it comes to elastomeric bearing, no painting should be done on top of that, even sort of to hide anything, and that is completely strict no. Uh, for metallic bearings to corrosion protection, there are there are several factors which account for the life of the paint film, and some research in US has shown that whatever painting we do for the metallic bearings, uh, 50% of the life of a paint film depends on the surface treatment, 20% on the thickness of the paint film, 5% for the paint type, and 25% for all other factors, that is construction, environment, steel surface conditions, etc. Uh, just to give you an example, sandblasting is what is conventionally done as a surface treatment for the metallic parts, but the recent trend is to provide water jetting, which is far too good, and in fact it is a better proposition than the sandblasting. And these are issues which needs to be taken into account in the manufacture of manufacture and corrosion protection of the bearings. Surface treatment using this ultra high pressure water jetting, it employs pressure of about 172 MPa, that is 25,000 psi, and this is a much better alternative than use of sandblasting. Coming to the last part, which is the installation fault, there could be several reasons for faulty installations: lack of clamping device or leaving the clamping device after installation, installation of bearing before compression of the bridge structure, lack of bedding material, wrong installation and non-respecting installation tolerances, non-parallelism of contact surfaces, wrong pre-setting of bearings. These are the seven reasons common installation faults, which if we can avoid, then we can prevent failure of the bridge bearings. So let us go one by one, on this lack of clamping device or leaving the clamping devices after installation. So what you see here is, the failure of the bearing due to lack of clamping device. You see, the pot bearing is an assemblage of various components which is put one over the other, and if they are installed, keeping these tolerances as it is, then only it will function. Now the clamping device helps to keep all these assemblage intact. So, and during the transportation and installation, that should not get disturbed. But in this case, because though no clamping devices were there, you can see that during the installation itself, half the things are coming out, causing failure. The other extreme is leaving the clamping devices after bearing installation, and which can lead to damages, at many parts in the plinth. And I have personally visited many existing bridges after 5, 6, 7, 10 years of its construction. And to my surprise, I have seen in many cases that the clamping device were still there, and nobody has removed the clamping device. This should have been removed just immediately after construction, before putting the bridge on service. These are again some examples of poor uh, you know uh, installation due to either lack of clamping device or not removing the clamping devices. This is a failure due to wrong orientation on unreleased transportation bolt. You can see that leveling and general installation failures here. Now, coming to installation of bearing before completion of the bridge structure, this is one example where a 7-span continuous structure during the construction itself, uh, you know, heavy damage uh, was there at the pedestal, and the reason for this damage was simply because the bearings were. This is a fixed bearing which was designed, which was at the abutment and designed for the service stage, where all the other supports were supposed to be free against any translation for temperature movements, etc. But during construction, uh, uh, this superstructure was on staging, and they were fixed at not one point but other point as well, and due to which the forces were almost 10 to 12 times the design force, and that caused the failure of the system. This is another very good example of a failure of a bearing during installation. Uh, this is a steel concrete composite bridge, 5-span continuous, and the stage of correct construction was that to first the girders, steel girders were installed, uh, and then the top deck slab was cast in phases. Now, unfortunately, the permanent bearings were fixed when the after the erection of the plate girder, which actually the permanent bearing should have been installed later. But the fallout of this was that during the stage construction, at one point of time when the deck slab was cast up to stage 5, the since the plate girder weight is much less as compared to the weight of the deck slab, there was an uplift, and the top plate and the uh, PTFE stuck to the top plate, got lifted up, and then before the next load comes, there was a temperature variation, and that caused the top plate and the PTFE to move with respect to the bottom plate. And when the stage 8 and stage 7 was done, and when it rested at a different position, causing collapse. You can see a photograph here to demonstrate what I'm saying. I'm talking about the bearing at abutment end. This is another failure of the elastomer. I think I have shown this slide earlier also. This is an elastomeric pad extrusion due to excessive deformation caused by high horizontal lateral load during construction. As I mentioned, during construction, if you do not release the forces properly, and if it causes very high forces, then it can cause collapse of the bearing. Coming to lack of bedding material, I think the best example I can give is that of Airport Link project, where of 86 spans, bearings for 86 spans were replaced, and these elastomeric bearings were replaced because the during the installation, the leveling pad and the mortar filling was not done properly at the top and bottom, as you can see here. Wrong installation and not respecting erection installation tolerances. I think Ultratanga flyover collapse, I mentioned earlier. This is a glaring example of interchanged bearing causing overturning. Another example is a bridge at Goa, Gondolin Bridge, Goa, which I had inspected for some, tilting of the top arch. But while inspecting the bridge, suddenly I found that the bearing at the fixed end, which was supposed to be oriented towards the, aligned towards the transverse direction, but I found that site is aligned in the reverse direction. And these kind of errors are not uncommon in India, I can tell you. And this shows that there is a need for very high degree of quality control in bearing installation. Another good example of poor installation is the Deravasi flyover in Punjab, where you can see that a normal pod bearing, the bearing sleeves are like this. It is embedded into the superstructure, and the bearing sleeve for the bottom plate is embedded into pedestal. And one is supposed to, thread this screw from the bottom, but the contractor installed the bearing top plate with sleeves upside down. You can see that the sleeves are visible, and they simply cast this cross girder by putting the bolt from the top, and this shows the sheer ignorance of the system. It's not just the authority engineer. The drawing shows, by the way, this only. It is not the mistake in the design here. It is the mistake of translating the informations given in the design at site, and poor uh, supervision by the concerned independent authority engineer. This is another example of failure of non-respecting installation tolerances. Uh, it concerns a position in plane as well as the incorrect positioning in height. So if you install knowing fully well that it is not in alignment with the support, obviously it will cause failure of the pedestal, or it will cause failure of the bearing. So I think these are very very important issues which should be addressed uh, during the installation process. The In case this kind of positioning problems arises, the matter must be referred to the design engineer. Coming to non-parallelism of contact surfaces, spherical bearings, you can see there is a slide which shows that if your top and bottom surfaces are not parallel and they are not leveled, it can cause at the installation stage itself a unacceptable rotation. You can see that already the top plate is rotated by a very large angle here, which is unacceptable. Wrong presetting of bearings. Let me tell you, presetting of bearing of sliding element used to be a practice. I think it is still a practice. Some people still do it, and it is done to reduce the design movement and the range of capacity of the bearings. Basically, you know, the bearing has to, the top plate of the bearing should be large enough to accommodate the translations due to creep, shrinkage, temperature, etc. Now, the inward movement is always larger than the outward movement, because the outward movement is caused by temperature, whereas the inward movement is because of temperature plus creep plus shrinkage, etc. So therefore, it is always a tendency, in order to reduce the size of the top plate, to do a pre-setting, which means that you 50% of the movement caused due to shrinkage and creep is is absorbed by pre-setting the top plate of the bearing. Now, the risk of pre-setting is that, if the installation is done improperly, then it can play havoc. As an example, you can see here the this is pre-setted bearing, where you can see the top plate has very large allowance here and a small allowance here, and actually this should have been done other way around. That means this large gap should have been here and the small gap should have been here, because this is the inward side. So such mistake in installation can cause havoc. So the suggestion is that avoid doing pre-setting. We need not, optimize to such an extent the bearing cost. The additional cost due to an increased top plate dimension is hardly anything, and it is better to avoid pre-setting unless you are 100% sure that you will be able to ensure a proper installation of the bearing. So, I've come to the end of my presentation. To summarize, I would say that the main reason of failure of bridge bearings is that they are still treated by bridge engineers as construction products, but not mechanical devices, where manufacturing tolerances are more stringent. The requirements for quality of modern bearings are much more rigorous as compared to the roller rocker bearings. Bearing inspection during manufacture, installation, and also during service should be done by learned engineers. At present, these are done mostly just as a perfunctory. Bridge designers need to be more aware of bearing behavior. Decision making for the choice of appropriate bearing type requires a lot of skill and experience. Designers need to take special care while carrying out the detailing of pedestal rebars and rebars of superstructure at bearing locations. Quite often, bearing installation becomes difficult due to fouling of rebars with the bearing studs. Clamping devices should be very firmly attached with the bearing parts and left in that position till the very end of the bearing installation. These devices should be removed when the bearing becomes functional. Bearings should generally be installed at the moment when superstructure is totally completed. Temporary bearings during construction stage, which can be easily removed after superstructure completion, should be followed. Pre-setting of bearings should be avoided as far as possible. It is recommended that bearings be installed under the supervision of manufacturer's representative or by qualified personnel from the manufacturer. Bridge designers are advised to have few good reference books in their library. Some of these are given here. List ACD 6, which is a IAStructE document, bridge bearings and expulsion joints by David Lee, and structural bearings by Helmut Igard, Wolfram Kauschke. So with this, I come to the end of my presentation. Thank you very much. And if you have any question and answer, you can email to me at bsec.ab@gmail.com. Thank you very much.